I believe we've admitted everyone. So good morning, everyone, and welcome to COVID-19 seminar. Today's meeting will be chaired by Jianhong Wu, and we have two speakers today, George Bucyibaruta and Charmaine Dean, who will be talking about predicting COVID-19 deaths and developing indicators for increased mortality. I will hand it over to Jianhong Wu.
Oh, thank you, Sarah. So again, on behalf of the Fields Institute, and would like to thank you all for coming. And today we have a presentation from the team of University of Waterloo and the leadership of Professor Charmaine Dean. It's a very strong statistic component of this Canadian COVID-19 task force. Charmaine is a key member of the team and a member of the executive committee. And I think this is the issue that the different public health agencies at different levels are key. And I'm very looking forward to the presentation. Charmaine, you want to introduce George as well? Or?
Sure. Thank you, Jianhong, for inviting us. Of course, it's a requisite for being part of this team to update everyone on the work that we've been doing and where we see opportunities for supporting public health work related to COVID-19, the very important issues that Jianhong and the team are trying to move forward on. This is work that's done jointly with George and Elizabeth, who are postdocs under my supervision, and I'll share the talk with George to give him an opportunity to present to an audience. George came to us from, well, most recently from Mexico, but he is from Rwanda. And what an unfortunate experience for him, well, for the world generally, to come and join a team for a postdoc and then immediately be dumped into no opportunities to work with his supervisor. So I'd like to share the presentation with him to give him an opportunity to say a few words in at least some sort of a venue in Canada. So as the title describes, what we've been looking at predominantly is how prediction of COVID deaths. There are a few things that are the aims of this work, and not all of them have been addressed in what we will present today. But I'll give you an overview of what we're trying to do, and then at the end of the talk, we'll come back to that. So we're looking at developing, and this is a different model. It's not a model that is a standard agent-based model, etc. This is a model that's basically an empirical model for predicting COVID deaths. What we would like to do is to do joint modeling of deaths plus cases plus hospitalizations. And we've come a long way in that regard. And then using a variety of tools, develop indicators for change, indicators for when curves start to go in a direction that indicates a differing trajectory than flattening, or when we are able to identify resurgences. So the principal aim is to use a variety of responses jointly and then develop indicators. And what this talk will do is it will indicate how far along that goal we have come. So as I said, the talk is about modeling deaths, and we're focused on the province of Ontario. It may be that we will look at British Columbia data because of the sharp changes that are happening there more recently that can identify whether some of the indicators will pick them up. But right now we're focusing in Ontario. The approach uses growth curve modeling, and we're looking at the cumulative number of deaths from COVID-19. Growth models, as you know, for example, George will talk about this in a minute, you know, an exponential growth model or a double exponential growth model. We need a growth model here that will accommodate that there's going to be a flattening. So a growth model that has an asymptote. And so a basic growth model with an asymptote is the logistic growth model. That logistic growth model has, the asymptote is defined as what's called the carrying capacity parameter. And carrying capacity is exactly that, what's the sort of the biggest that this can blow up to. So that's the idea behind the carrying capacity parameter. The basic logistic growth model has a fixed carrying capacity parameter. That means that the asymptote is based on a quantity that is a fixed value. We know with infectious diseases that the carrying capacity parameter, the sort of biggest number of deaths we can see at any time period, is going to change over time. So this growth model needs to have a carrying capacity parameter that will change over time. And as I mentioned, this is not a process model, but we're playing with an empirical model. The key is, so one of the keys is to link outcomes jointly. And another key, I'll talk about that at the end. Another key is to develop an indicator of change. So that indicator would be linked to resurgence of the disease. We want to find alarm functions and triggers for the alarms that would serve as markers for some sort of public health intervention. And we utilize Monte Carlo methods to be able to get confidence bands for some of these indicators. So we're using a logistic growth model with a modification so that the carrying capacity parameter will vary over time, and then use these to develop indicators.
The basic model for modeling the population growth is an exponential growth model where the per capita growth change is basically a constant over time. In the other hand, the logistic growth model should be used where the logistic growth model has an asymptote or a parameter that's known as the carrying capacity, which allows the growth to be limited at a certain level. So this is a classic logistic growth model where this carrying capacity also is considered as a constant. Now, let's look at our proposing model where this expression one representing the change of cumulative number of deaths over time, and also, as we mentioned, the carrying capacity or the asymptote, upper asymptote is being considered as a function of time. So here, our N of T is standard for the cumulative number of deaths, and N naught is considered as the cumulative number of deaths at the initial time. This differential equation has a solution in this form expressed in form 2, where the big input is this function k. So next slide will express the function that representing the k, where, as we mentioned, also we are modeling k as a logistic growth curve. At this time, k as well has its own carrying capacity that is represented as G. So the general solution of our logistic growth model with the logistic varying carrying capacity is expressed in this form 5, where this function has different parameters to be estimated. So the approach of estimating this parameter as we adopted the nonlinear least square approach as our cumulative function f representing the growth curve model is a nonlinear function. So the basic way of estimating a nonlinear function or linear function is just this way of minimizing or optimizing the residual sum of squares. So in our case, the parameter theta is a vector parameter that contains those different parameters from the logistic growth model.
So as George indicated, using a logistic growth model with a carrying capacity parameter, which as I mentioned at the start, right now we are viewing it as logistically varying, but we would like to change that, and I'll come back to that at the end. This logistic model will give us an estimate of the future mean cumulative number of deaths. But if we would like to simulate future deaths, we also need to incorporate the variability observed in daily deaths in order to use a Monte Carlo approach for future daily predictions. And to do that, we use an approximation of a negative binomial model for daily data and estimate the negative binomial dispersion parameter using that approximation. So then for simulating future trends, we use a Monte Carlo approach where the mean is derived from the fitted logistic growth model for cumulative death, and the variability is derived from the estimate from the negative binomial model of the variability in the daily death. Using this Monte Carlo approach, we are then able to simulate future cumulative deaths to be used then for our indicators to model future trajectories. So remember that we've used a logistic growth model where at any point in time, the carrying capacity for the number of deaths, the cumulative number of deaths, is based on a varying logistic model. What we really want to do is to define the carrying capacity as based on some conceptual framework that makes sense for COVID. So for example, you might think that the limit in the number of deaths at any time should depend on cases, or it should depend on hospitalizations, given that hospitalizations reflect the severe cases. So again, let me say that what we've done is not yet modeling hospitalizations, and I'm going to come back to that. The next step is then, if we've got a model that represents the cumulative growth effectively, then what we want to do is we want to develop indicators for change. So those indicators can be based on, we've seen lots of indicators that are based on the cumulative number of deaths. They are, how do we compare deaths in the next 3 days with what has happened in the past 3 days? You can also base the indicators of change on the change of deaths. So this whole model started from a differential equation, which modeled the rate of change of n with t. So we could also develop an indicator that monitors how the NDT is changing. So is the NDT 3 days ahead less than what it is today? Or 5 days ahead, is it continuing to be less than what it is today? And then finally, if we use hospitalizations or cases or some other response variable for carrying capacity for COVID deaths, then we're also able to use an indicator based on the carrying capacity parameter. So, is the hospitalizations changing too rapidly? So it could be based on the carrying capacity K, or it could be based again on the change of K with T. So all of these are potential indicators of change, and the intention here is to use change indicators jointly, so not single indicators of change. And so with a Monte Carlo approach, it's reasonably easy to estimate probabilities of indicators meeting a threshold. So all you need to do with a Monte Carlo approach, of course, is basically a counting process. How many times did the trajectories achieve the threshold? Or if you have a series of thresholds, how many times did each of them happen or are predicted to happen over the next 5 days? And so you can tease this out with one particular threshold. Is the counts going to increase above a threshold that you're not happy with? Or is the rate of change going to increase? Or is the number of hospitalizations? Or you could use all three together to form a joint probability statement in an alarm function.
So the following, we are presenting the data that we'll be analyzing in this talk. So basically, we are using cumulative data from Public Health for Ontario, where in the left-hand side, we present the cumulative death in Ontario, and on the right-hand side is the plot for daily deaths in Ontario. So these data are from 17th March up to 17th July. So here we present the fitted curve from our logistic growth curve with a varying carrying capacity in red, and the black is the curve for observed cumulative death in Ontario. So our logistic growth curve model looks good in terms of fitting. So in the next slide, I will be presenting some more assessment of the presented model in terms of predictions. But here is the other way, just to present the data or to present the fitted model as the previous slide, which also we should appreciate the way our model is fitting the data. So here is just some assessment in terms of predictions. Basically, what we are doing here, we have 4 columns, where the first column is indicating the initial date or the baseline date. So the second column, we have the corresponding cumulative number on that date. Then we are assessing the predictions within 5 days ahead. So the third column is indicating what we predicted under the our logistic growth model. And the last one is the cumulative number of the cumulative death observed. So as you see, the differences between the predicted within 5 days ahead and the observed, the difference is being decreasing as the number of observation is also increasing. So basically, this due to the quantity of observation that have been used when we are estimating the parameter of the model. So in this plot, we present as well the simulated from negative binomial distributions, and also we are showing the mean curve of logistic growth model. The red curves indicating the simulation of future cumulative death, for which will be used in the next slide in terms of calculating some indicators.
I think we are all fairly familiar with the first indicator here. The first indicator essentially says, you know, what's happening 3 days ahead should not exceed how many deaths happened in the last 3 days. So you want that the number of deaths at T0 plus X, so X days ahead, to be not in excess of the number of deaths that were 3 days previously added to the current number of deaths. So you don't want the number of deaths to be greater than what's happened in the past 3 days, essentially. And that indicator has been used several times in the literature, and it's a common indicator in the current COVID context. As I mentioned, what we'd like to do is develop a few other indicators and also include indicators related to hospitalizations and/or cases. And so another indicator that we might be considering would be suitable here is, this is all based on a differential equation model for the rate of change of N of T. And so you might think that what you would like in the future is to ensure that the N of T is less than what's happening currently. So the rate of change of N of T with time at the current time should not exceed 5 days, what's happening 3 or 5 days ahead, depending on what X is, what your window choice is.
Now let's take an example where we consider our initial time T naught to be day 54, which was on date 19th May 2020. So on this date, the cumulative number of deaths was 96.2. So as we said, here we consider two kind of windows. So we will just assess a window for 3 days and the other one for 5 days. So starting with the window of 3 days before, so 3 days. So those are this one correspond to days, day 52, 53, and 54. So that is considered to be the previous window to time T naught. So in these windows, the number cumulative death that has been observed is 81 deaths. So if we add those 81 deaths to 1962, we'll have 2043 deaths, which is our limit. So we want to assess whether within next 3 days ahead, if the number of cumulative deaths will not exceed this number. So the estimated probability for which this will happen is equal to 0.71, means that there is approximately 30% of chances for which this will not happen. So on the other side, when we consider, for example, a window of 5 days, the estimated probability was 0.86, in which the cumulative number of deaths within next 5 days will not exceed 99, but also there is approximately 14% of chances that this one will not happen.
So that also points to another issue with the development of an alarm function. So what we have here from fitting the model, running our Monte Carlo simulations, it shows that there is a 30% chance that the number of deaths will exceed what's been seen in the last 3 days, and a 15% chance that the number of deaths will exceed what's been seen in the last 5 days. And then, of course, the question is, what's the probability threshold? And I'm going to come back to that after I give George a chance to review a second example. So in actuality, 30% and 14% are too large. So in fact, the number of deaths did exceed what happened in the last 3 days on the 19th of May. And again, the number of deaths did exceed what happened in the last 5 days on that date. So that 30% chance is pretty high for an alarm function. And so is the 15% chance. So, George.
Okay. So let us consider the other example. Similarly, here we consider T naught to be 17th July 2020, where we are considering the cumulative number on that day to be 2748. So within a window of 3 days, the estimated probability of not exceeding that cumulative number of deaths was 0.99, means that we have also approximately 10% of chances to have a different result. So for the window of 7 days, so also the estimated probability was 0.96% of chances to have this, for which this to happen. But also on the other way around, you have almost 4% of chances for which this will not happen.
Just repeating what George said there, a 10% probability that you won't exceed the number of deaths that happened in the last 3 days, and 3%, 4% probability that you won't exceed. So you might remember when we were in the May period, end of May period, those probabilities were much higher. And now these probabilities are much lower. And in fact, we did not exceed in Ontario the 3-day number of deaths at this time on the 17th of July, and neither did we exceed the 2773 mark for the 5-day window on July 17th. So here's the issue. What is the right probability threshold? Obviously a 30% chance is high, and a 5% chance seems like it's meeting the mark. There is a technique in biostatistics that's called receiver operating characteristic analysis, where you can do this sort of analysis for a whole series of dates and develop these probabilities and compare with what actually happened and get an optimal value for an alarm threshold. And so that's what needs to be done here in order to conclude this section of the work. So we have these probability thresholds. We can get them through Monte Carlo simulation. And what we need to do as a next step is, using the most recent historical data, develop a threshold that is optimal using receiver operator characteristic analysis. So I also talked about indicators. This is a regular indicator, what's happened in the last 3 days. What we want to do is to go beyond that. And this whole model is based on the rate of change. And so it would make sense to develop an indicator based on the rate of change. And we know that the rate of change the counts can change sharply over a short time period. We've seen how the trajectories are changing in BC and a few other places. And so there could be an opportunity to look at instead the rate of change. And so this is the rate of change function. And we've also drawn lines on the curve to show how the rate of change of NFT has evolved over time, and where phase 1 for Ontario reopening started and where phase 2 for Ontario reopening started. And of course, we're happy to see this rate of change curve drop down to 0. But what we would like to do is develop an alarm function based on this. And again, the alarm function will have the same characteristics. We would be looking at historical data to look and see whether or not the change is 3 days ahead is less than the rate of change at the current time. How applicable that will be as the rate of change flattens out is unclear. But then again, using receiver operating characteristic analysis, develop a threshold by which those probabilities will change into alarm functions. And then based on a variety of indicators, look at them jointly. So instead of looking at one indicator, look at 2 or 3 indicators jointly. And at this moment, we're thinking of the rate of change function. We're also thinking of the cumulative number of counts. And then in the next slide, I'm going to talk about hospitalizations. So this model has a very nice conceptual interpretation for the carrying capacity parameter in the logistic curve. That carrying capacity parameter is, what is the carrying capacity of deaths? What's this maximum number of deaths that you can expect at a particular time point? And we would like to tie that to the number of hospitalizations. So right now, what we've done is we've estimated it empirically by using a carrying capacity parameter that's a function of time. Some might think that that should be based on a number of cases, not the number of hospitalizations. So we could explore using the number of cases. The reason we think hospitalizations would be better is that, as we know for COVID, many of the cases are very mild, and it is the hospitalizations that are more strongly linked to the severe cases that progress to death. For historical analysis over Ontario, using hospitalizations has limitations because not all the deaths occur earlier on, not all of the deaths occurred in hospitalizations because of the issues with the long-term care facilities. So that's a challenge here. We have used hospitalizations in this logistic model. And the way we incorporated hospitalizations is we used another logistic curve to model hospitalizations. And you saw that very nice match between predicted and observed in this logistic model. Well, that was absolutely not true when you use hospitalizations as following a logistic curve. And we have tried using raw hospitalization values, so not modeling it at all, just using the raw values as a carrying capacity parameter. And that fits a bit better, but it does need to have its variability removed. It does need to be modeled. More recently, as in last week, we have developed a good model for hospitalizations. And that is it's a generalized logistic rather than the logistic that's being used here. So it has a bit more flexibility. And so at this point now, we will be incorporating that model into the logistic model. So at this point, we will have a model that jointly considers deaths and hospitalizations. I mean, obviously, this is an empirical model. And so it's not meant to be on its own. It's just meant to supplement all the other outstanding work that's done that use agent-based models or models that account for mechanisms of transmission. Those are really important because then you can change all of those mechanisms and then understand what's going to happen in the future. This model doesn't do that. It is another tool that we think is useful. It has a simple interpretation. The landing point of this model will then have both deaths and hospitalizations in a single model. It'll have an alarm function. It will use Monte Carlo estimates to then create probabilities related to alarms being triggered, and then it will have thresholds related to these alarms. It has lots of limitations. I've talked about some of them already, and also limitations related to the data. And then the final point that I'll mention is that it may, I mean, it's likely going to be more important to take the model in its entirety and use it for regional analyses. We know that there are regional differences in trends, and so it may be more interesting to be able to develop alarm functions for regions rather than the province as a whole. Looking into the fall, for example, as schools start up and other activity happens in the province. And so that, I think, concludes the talk, and there's some key references that have supported baseline analyses in this work, and so I've listed them here. So for Jiang Hong, in terms of our contribution to the project, where we're going, we do have the model for hospitalizations. We need to incorporate it. We have incorporated raw values and they don't work as well, but we think this model will work now. And then we do need to create this threshold for the alarm function, and then using the thresholds jointly is easy because we're using Monte Carlo work. So anticipating something like, I don't know, maybe 2 or 3 more weeks before we finish. We've already started writing up the work into a paper. And so looking to wrap this up probably in 3 weeks and then submit. Thank you very much, everyone, for listening to our contribution to Jian Hong's project.
Thank you, Charmaine, for a very, very interesting talk. And before I open the forum for discussions, I will comment about the ongoing project of using this to model the hospitalization. I think that's going to be very important. And I know there are a couple of studies, I don't know if they have published or not, but they are really looking at the correlation between the capacity for a nation to increasing its ventilators and hospital bed and the mortality rate. And so it was observed in several countries that facing the COVID pandemic in the first few months is the capacity of the nation to increase its medical resources that really had significant impact on the mortality rate. So I think what you're doing could be very useful in that sense. Thank you, Charmaine. And then the other questions, maybe I will start with a question from Niana. I said Deanna. I think, Niana, you raised these questions in the middle of the talk, so I only allow you to do now. Niana, are you able to raise the question directly?
Yeah, so I actually, maybe I kind of thought about the answer, but I'll just maybe kind of put my ideas out there. I was wondering if the impetus you had for the assuming that your model doesn't actually have more deaths than, let's say, 3 days previous to that, or 3 days or 5 days before that, for instance, is this due to what you saw in the data in the sense that like your number of deaths can only get so big, or is this following the actual logical trend that you need to see a number of cases rise before the deaths would occur, like let's say several weeks later? Is this due to the actual data, or due to the actual trends in the observed deaths globally, where you actually see the deaths lag significantly behind the actual number of cases?
Okay, so that's a really good question, and thank you so much for that question. Jian Hong, we actually have a second project on this work that looks at hospitalizations, lags of hospitalizations and deaths. And Liz, could you talk a little bit about what we're seeing in the data with regard hospitalization, lags, and deaths in the future? You've done a thorough analysis on that.
I know two projects. One, the project was involved is to compare the capacity of different countries or different regions to really increasing its hospitalization bed, ICU beds, and PPT, and also the ventilator especially. how it's correlated with the change of mortality rate in the first wave, really. So I think I don't see much study in the literature about how the increase of this capacity, how this is going to impact on the mitigation of COVID. So this could be, I think, a very important area.
I have another question, if that's okay. So there was a kind of data on the number of daily deaths that looked kind of like it was a bit sharp in the sense of like the trend. I don't know if I can find, if you can find the this slide. So when you're talking about the rate of, when you talk about the rate of deaths, you're not referring to daily deaths, right? Because I would imagine if you want to differentiate over something that looks like this, where it's kind of jagged, it's kind of hard to put a model on this since it's not smooth, right? That was my other question, basically. Like, how do you?
Yeah, that's why we use the cumulative deaths instead. The cumulative deaths are more amenable to smooth function rather than the daily deaths. But we could obviously take, George, if you go back to the fitted model, we could use the fitted model and superimpose the fitted model by differentiating on the daily deaths as well, to see how they mesh. And in fact, as we were preparing for this talk, I suggested that that should also be included, but we ran out of time.
Cool,
So,
thank you.
Good point.
Now I have a question from Monsieur Effendi. Monsieur, are you able to raise the question directly?
Yes, thank you very much for a nice talk. This really is very important. The question is the following, as far as concerned to the modeling. So the indicator that the carrying capacity depends on time, it's in some kind of indicator you would like to introduce some stochasticity. Why not to consider the for the carrying capacity single stochastic differential equation? I mean, you have a couple. This is the one question. The other question is that actually last week gave a talk your colleague from University of Waterloo, who considered the case when the carrying capacity could depend also on location. So there's such a kind of the heterogeneous effect. How you can comment these two things? The one is to consider not double the logistic, instead of consider the single, adding single stochastic differential equation. As second, the effect of heterogeneity, because last week it was a very good indicator that the total population, the cumulative number could exceed with diffusion rather than without diffusion. Thank you.
So I think that, Masood, that is a good idea, using a differential equation model for the carrying capacity parameter. And I do believe that George has looked at that and actually not seen as good a fit here, but it could be because we haven't explored it thoroughly enough. But it is something that we think as well is worth exploring. And you're completely right about local effects. You know, Liz has mentioned that in several conversations, that we need to break this down into local regional effects rather than looking at all of Ontario, because there's so much disparity, or as you call it, heterogeneity across the province. What might be interesting to do when we were thinking about that is how to cluster the curves across regions. So if there are ways to cluster the curves in regional effects into even three categories, you know, is three different clusters. One where things are obviously, if you look at the NFT curve, where things are actually sharply decreasing in in a certain way. This is the overall province. You might be able to see rates of change far sharper in some regions of the province, and then harder, not as good in some other regions of the province. So if we broke this down into regional effects, then there's also the opportunity to cluster the regional effects into, you know, some basic clusters. Let the data identify how many clusters there are, or just look at 2 or 3 clusters and see we want to look at where rates of change are really sharp and slow, or rates of change that are just not flattening as we would like. So that could be an opportunity with a regional model.
Thank you.
I should have one more question for you, Georgia and Charmaine, is I understand if this is the hospitalization, I know the carrying capacity. So in the model for the mortality, what are you talking about, the carrying capacity for the death, or really what carrying capacity is interpreted here?
So the model for the deaths as we currently have it or currently envision it is a model that has, so the logistic growth curve model has, at each point in time, you have a carrying capacity parameter. We envision that carrying capacity parameter as hospitalizations, because hospitalizations are the more severe cases. Initially, we thought the carrying capacity parameter should be the number of cases, but as we know, as I said, the number of cases doesn't make sense here because there are too many asymptomatic cases. There are too many cases that have very little things happening. And then we have a cluster of individuals who have characteristics like age or vulnerability that lead to hospitalizations that then have a high risk of mortality. So that's why we felt that the carrying capacity parameter for deaths is hospitalizations. And then now you've thrown in this whole other idea that if we use a model that has a differential equation that's similar to this for hospitalizations, then we will need a carrying capacity parameter for hospitalizations. And clearly that's going to be the capacity of the hospitals. And which you say could also be changing over time or could be fixed over time, depending on, choices that hospitals make. So that's the framework. I think Liz mentioned to us that we should figure out what's the capacity of the hospitals and build that in. But in terms of wrapping up this paper, we weren't thinking of including that. But I mean, if it makes a lot of sense, then we could go back and fit that in.
Thank you. So are there other questions, comments? So if not, then let me first of all thank on behalf of Field Institute and especially Kuma, thank you, Charmaine, for your team, and we're also now members of this task force commissioned by the institutes have been very busy with the own responsibility to different provinces and to federal agencies, and we are in a relatively calm stage. So I think the task force is going to intensify the discussions and planning for the next phase of more team effort. So I think it's very good to hear some of the presentations from members of this task force, and we want to have more discussions both formally and informally, and I encourage other members of the team to join this. Again, thank you, Charmaine, thank you, George and Elizabeth, for your team effort.
Thank you, Jiang Hong.
Thank you, Jana.
Thank you.
Okay. Bye.
Bye.
Everyone.